In this lesson, we are going to work on the expansion of binomial algebraic expressions in the form a plus b to the n, where n is a natural number. We are going to start by observing the pattern in the expansion from n equal to 0 to n equal to 3. For n equal to 0, a plus b to the 0 is equal to 1, as any non-zero real number to the power of 0 is 1. For n equal to 1, a plus b to the 1 is equal to a plus b. Looking at the coefficients of the expression, both a and b have a coefficient of 1. For n equal to 2, we have a plus b squared, which is equal to a squared plus 2ab plus b squared. Now looking at the coefficients, a squared has a coefficient of 1, ab has a coefficient of 2, and b squared has a coefficient of 1. Now for n equal to 3, a plus b all cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. Now looking at the coefficients again, we have the coefficients 1, 3, 3, and 1. Let us stop here now and try to check for a pattern in the coefficients. Taking the coefficients aside for their corresponding values of n, I first notice that the first and last coefficient in each row are always 1 for every value of n. As for the coefficients in the middle, I first notice that 1 plus 1 is 2, then 1 plus 2 is 3, and 2 plus 1 gives 3 as well. And if I continue with that pattern for n equals to 4, the first and last coefficient should be 1, and in the middle, I add 1 and 3 to give a 4 for the second coefficient, then 3 plus 3 to give a 6, and 3 plus 1 to give 4. Again, for n equals to 5, the first and last coefficient should both be 1, and then 1 plus 4 gives 5 for the second coefficient, 4 plus 6 gives 10 for the third coefficient, 6 plus 4 gives a 10 again for the fourth coefficient, and 4 plus 1 gives a 5 for the fifth coefficient. And so on. Now this is what we call Pascal's triangle, which would help us find the coefficients of the expansion of a plus b to the n. Now that we have found the pattern for the coefficients, let us try to find the pattern for the rest of the terms in the expansion. We first notice that for every value of n, the first terms are a to the n, and the last terms are b to the n. So for a plus b to the 1, we start by a to the 1 and end with b to the 1. For a plus b all squared, we start with a squared and end with b squared, etc. But what about the middle terms? Looking at the exponents of a in a plus b all squared, we notice that we start from a squared, the second term is a to the 1, and the last term has no a, so that's as if we have an a to the 0. Similarly, looking at b, we notice that the second term has b to the 1, and the third has b squared, but the first term has no b in it, so this is as if we had a b to the 0. We kind of caught a pattern here. For a plus b all squared, we started with a squared and decreased the exponents of a all the way to a to the 0. As for b, we started with b to the 0 and increased its exponent all the way to b squared. Let us see if that works for n equals to 3. We notice that a starts with a cubed, then we have a squared, then we have a to the 1, and there's no a in the last term, so that is a to the 0. And again, as for b, we start with b to the 0 and increase all the way to b cubed. Then the pattern is found. As we already found the coefficients corresponding to n equals to 5, and we now have the term pattern, let us try to expand a plus b to the 5. For a, we start with a to the 5 and decrease the exponent of a all the way to a to the 0. For b, we start with b to the 0 and increase the exponent all the way to b to the 5. And according to Pascal's triangle, the coefficients for n equals to 5 are 1, 5, 10, 10, 5, and then 1. And adding the terms, we now have the expansion for a plus b to the 5. But what if I'm asked to expand a plus b to the 16? Should I go on with Pascal's triangle till n equal to 16? And what if the exponent is even bigger? In this case, Pascal's triangle would no longer be practical. We need a way to find the coefficients of the row corresponding to n equals to 16 without having to find all the previous rows. That is in fact done using combinations. Recall that if you have n total objects and you wish to select groups of R objects without taking order into account, the number of groups that can be formed is given by the combination of R out of n denoted by CRn, and it could also be denoted by a vertical vector with n at the top and r at the bottom, which are equal to n factorial divided by r factorial times n minus r factorial, given of course that n factorial is the product of consecutive integers from 1 to n. Now the values of the coefficients in Pascal's triangle are in fact combinations. Let us take an example to see how they work. For example, for n equals to 5, we know that the coefficients are 1, 5, 10, 10, 5, and 1, as found in Pascal's triangle. Since n is equal to 5, then all these numbers are combinations with a total of 5. As for the number of selections, the first one starts with a number of selection of 0, the second one all the way to 5 for the last one. Evaluating those combinations using the formula or the calculator would give us the coefficients of Pascal's triangle for n equals to 5 without having to find all previous rows. For example, if we were to evaluate together the combination of 3 out of 5, according to the formula, that would be 5 factorial divided by 3 factorial times 2 factorial, and applying the factorials, which means 5 factorial being the product from 1 to 5, 3 factorial being the product from 1 to 3, and 2 factorial being the product from 1 to 2. So that would in fact be simplified into a 10. Now notice that Pascal's triangle is symmetrical. Then you could only find the combinations corresponding to the first half of the row, then finish the row by symmetry. Now, if we were to generalize a plus b to the n using the previous work, it would in fact be equal to the sum of the combinations of I out of n times a to the n minus I times b to the I, where I goes from 0 to n. That is known as the Binomial Theorem or the Binomial Expansion. Now this may look a little intimidating, but there's nothing to worry about. This is exactly the patterns we observed and worked with. Let us see that for n equals to 5. So considering the binomial expansion formula for a plus b to the 5, where we replace n by 5. Considering the terms for I equals to 0, I equals to 1, all the way to I equals to 5, you can actually see in the sum that the pattern is no different than what we have previously discussed. A starts with a to the 5 and decreases in exponent all the way to a to the 0. And b starts with b to the 0 and increases in exponent all the way to b to the 5. And the coefficients are taken as combinations of I out of 5 for each value of I, which in fact gives the expansion of a plus b to the 5 as we have already previously derived it. Let us now expand 1 minus x to the 6. As we need this in the form a plus b to the n, then 1 minus x can be written as 1 plus negative x. We are considering 1 for a and negative x for b. As we have previously seen, as n is 6 here, a, which is 1, starts with an exponent of 6 and decreases an exponent all the way to 1 to the 0. Then b, which is negative x, starts with an exponent of 0 and increases an exponent all the way to negative x to the 6. As for the coefficients, since n is here relatively small, you could use Pascal's triangle to retrieve the coefficients corresponding to n equals to 6. Or you could also use the combinations with a total of 6 with a number of selections starting from 0 all the way to 6. That sum starting from I equals to 0 all the way to I equals to 6 is actually given by the binomial expansion for n equals to 6, a equals to 1, and b equals to negative x. Now simplifying the expression gives the expansion of 1 minus x to the 6.